They're electrons. One of them is spin up and one of them is spin down. They have what's called a spin quantum mechanic number. And it turns out that electrons have a half spin. Now what that means is this. Has anyone here had physics? No, one person. So as an electrical field turns to the right, which way does the magnetic field point? Up. Right hand rule, right? You have to put the left hand in the pocket. As the electrical field turns to the right, the magnetic field points up. So what's going on inside of an atom is an electron is rotating, creating a minor magnetic field. Now, as this electron rotates down, what happens to the magnetic field? It does just the opposite. They cancel each other out because magnetic fields are vectors. All right? So that's where the term spin comes from. They're actually turning, kind of. See, quantum mechanics is so hard to explain to anybody. Never mind someone that's just first seeing chemistry. Because electrons are really not spinning like a top. That's just not happening because electrons look like a wave. They're vibrating like a violin string or a guitar string once you pluck it. That's what the little bitty electron would look like if you could get eyeball to eyeball with it, which you can't, because if you could get eyeball to eyeball with it, that means it would be completely stopped, and then that enters into all kinds of trouble, all right, with Heisenberg uncertainty and all that. So it's really hard to explain that, but they call it spin up, spin down. Okay, are we happy? Now, how does that get into this? First off, this is the S block. Blue, S block. How many electrons can be in an S orbital? 1, 2. 1, 2, 1, 2, 1, 2, 1, 2. You with me? Are we happy? What's next? P. How many electrons can be in all 3 p orbitals? 6. Okay, here we go. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's your P block. Okay. D orbitals. How many electrons can be in your D orbitals? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You get it as you go across here? What about F orbitals? 14. 57 minus 70. All right. That's your F block. All of this stuff is coming together. Now this is pretty amazing. I know you guys are so young and you probably don't care about physical chemistry. But look at this. There's some joker named Mendeleev, some real old timer, who just kind of placed this thing together based on the atomic mass of elements. Okay, years pass. People shave their beards, put on normal clothes. Here comes cars and all this. Then in the 20s, Edwin Schrödinger solved what's called a Schrödinger wave equation that mathematically placed the electrons in exactly the same place. All right, does that make sense to you? I mean, that's pretty amazing to me. Maybe it's not to you. To show how mathematics can be tied to this chemistry. I mean, it's all connected, right? And if you guys study chemistry long enough, you can solve like Schrödinger's equation for a hydrogen atom. Well, Schrödinger made the equation for the hydrogen atom, but you couldn't solve it because you need other equations to solve it. Well, it turns out that they started looking, and there was a famous mathematician who I think lived in the 16 to 1400s era called Hermite. And guess what he done? He solved all the equations for the hydrogen atom. They're called the Hermite polynomials back in the 1400s before anybody even knew that atoms were around. All right, he didn't know what he was doing. He just played the numbers game, found patterns. So that's pretty amazing that these mathematics guys and these chemist guys are kind of jiving and they really didn't know it. All right, so that's what we're dealing with here. So the next thing is we want to build our atoms. All right, and we want to see what an example atoms would look like. Now what I would like for you to do is to hold your questions for about 5 minutes. So in other words, even if you don't understand what I'm doing, That's just fine. You just sit there, bite your tongue, and don't say nothing. Because this is all about patterns. And if you give yourself 2 or 3 times to get the pattern, you'll be good to go. Now, certainly after 5 minutes, open up, right? We'll answer anything you want. Now, the first thing I'm going to do is I want to know what my lithium atom looks like. I want to know where the electrons are at, and I'm about to get a shorthand notation for that. Do not get scared about this. It's just shorthand notation. All right, lithium, where's it at? That's the first thing. Oh, right there. Okay, that means it's got 3 electrons in it. Okay, how do you read a periodic table? You read it from the left to the right, just like you read a novel. And when you get to the end of the line, you turn back around and just start here left to right again. Okay, so the first thing that my finger is passing through is the number what? 1. So let's stop and write that down. Now the second thing my finger is passing through is what type of a block here? S. Now, this is called, now if we had a 1s1, that would imply that there's 1 electron in an s orbital in the first energy shell. Are you with me? Now if I stopped right there, which I'm not going to, what atom would that be? Hydrogen. That would be the electron configuration of hydrogen. Okay, I don't want that. Let's make it a 2. That's a 1s2. Now if I stopped right there, what would that be the electron configuration for?
Helium.
Helium, right? Because get it? Last time we talked about how these little numbers here are the number of protons, but they're also the number of electrons in a neutral charge atom. Okay, so now we're at helium, as John tells me. All right, one more time down. We're coming into what row now? 2. So now we're at a 2. And then a what? S. That's where my fingers are passing. And how many electrons do I need there?
3.
Oh, now come on. How many total electrons do we need? 3. Well, how many have I already got there? So I can just add 1 more. So what does lithium look like? If you could get eyeball to eyeball with lithium, here's what you'd be dealing with. You'd have yourself a hard nucleus with a ball. And inside of that ball would be embedded 2 electrons. They are right here. You with me? And then you're going to have another ball that would be bigger. Now how do I know that that ball is bigger? Because it's got a higher number. See, the higher that number is, the more energy it's got, the bigger the ball is. So now we've basically got ourselves a ping pong ball that is inside of a beach ball. And how many electrons is there? Just 1. So that's what the atom of lithium looks like. If you were the atom of lithium, which one of these electrons is going to be what's doing it for you? That one on the outside. You see, these right here are protected, if you will, from most chemical situations. All right, so this is the electron configuration for lithium. Now let's try the electron configuration for oxygen. All right, again, I'll do another example or 2, and then we'll open up the floor and get some things cleared up. First, you start at the top left-hand side. Always. Okay? So here we go with the finger. I am in what? 1. And what block? S. Okay, so that's going to be a 1s. How many electrons do I need there? 2. Can I put 3? No. Can't have more than 2. All right. So that's a 1s2. Now, where am I at? I'm in helium. That's a number 2 there. Okay, back around we go. So that's a 2. S, what? 2s, 2. All right, let's stop. What atom am I located on if I stopped right here? Beryllium. Be. Do you see that? 2 plus 2 is 4. The number of electrons is the numbers up at the top right. All right. Now,